Okay, so now let's just do a couple examples. Uh, so we got a beam here. Fulcrum. We'll say there's a full force of, I don't know, uh, 25 newtons. And here there's a force of 12 newtons. The distance from here to this force, so we'll call this force 1, force 2. This distance we'll call d1 is 25 meters or 28 meters, and this distance 2 is 36 meters. I don't know. Okay, so the first things you do, so we know that first we gotta let's balance the forces. So the net force in, since there's no horizontal forces going left and right, we'll just stick with the vertical. Okay, so we'll call this, all the forces going up are going to be positive, all the forces going down are going to be negative. It doesn't matter which way you do it. Okay, so net force is going to be force 1 plus force 2 plus the force caused by this fulcrum here, because it's pushing up on the beam itself. So the net force on the actual beam, we'll call this F3 plus F3. Okay, and we'll say that the beam is in equilibrium. As far as it's in equilibrium as far as the beam going up and down vertically. So all together. So it could still be rotating, but as far as the center point, this whole thing is not being pushed down altogether. It's not falling. This whole thing's not going up. This whole system. I'm not saying that the beam itself is not turning or spinning. We're just saying that there's no movement in the vertical direction as far as the fulcrum. Okay, so our force 1, which acts downwards, negative 25 newtons, plus our force 2, which acts downwards, negative 12 newtons, plus force 3. We know that that's equal to mass times acceleration. So we'll call this the y direction, mass acceleration in the y. And we know that that's equal to 0 because, like I said, it's not moving up and down. So then we have negative 25 minus 12 plus F3 equal to 0. So bringing these to the other side, isolating for F3, we get 25 plus 12 is 37 newtons. So the force from the fulcrum, so it's pushing a force of 37 newtons. So if you imagine this whole thing as uh, a very tiny little box or just a ball, so there's force of 12 newtons plus 25 pushing down, so 37 newtons, and we found that there's a force from the fulcrum pushing up at 37 newtons. And this holds because the object isn't going up and down. So now what about the moments? So if the question tells you that beam is in equilibrium as far as moments or rotation, then you can immediately assume that the net moment or torque is 0. But if it doesn't say that, then you have to check to see if this is the case. Okay, so this is how we check. So you know that we'll say counterclockwise or clockwise is negative, and then counterclockwise is positive. It doesn't matter which one you choose. So the net torque or moment is the torque caused by force 1 plus the torque caused by force 2. And we know the formula for moment is just the force times the distance to the point of interest, or in this case, our point of interest is to the fulcrum. So that's equal to so force 1 is causing a clockwise rotation. So that's going to be negative 25 times, and distance this force is away from fulcrum is 28 meters. Then you add plus, so that was T1, tau 1, so plus tau 2. So it's 12 because it's causing a counterclockwise rotation times d2, which is 36. It's equal to, let me just punch down the calculator. 25 times 28. So negative 700 plus 432, and you get negative 268. And if you ever forget the meters, you know that force is in newtons, distance is in meters. So it's a newton meter. So what does this really mean? So let's separate the sign from the number. So we can conclude that there's a moment of 268 newton meters in the negative direction, and we know that negative is the clockwise direction. So 268 newton meters clockwise. So the beam will it will drop from the right side and rise from the left side. So it'll be a clockwise rotation. And essentially that's how you solve all the questions. So whether it was something like this, which I could do as another example, you got a force going like this, force going like that. These are the same thing. So the forces going down, this one, plus the forces going up, which is this and this, have to equal to 0. And the moments about this point, above the fulcrum, have to be 0. Or if they're not, they have to be 0 if the moments are in equilibrium. But if the question doesn't tell you that, and it tells you is it in equilibrium or is it rotating, then you just use this. You take the net moment or torque and use this formula. So basically all you need is F equals ma for this one, and you know that this is using the equilibrium, so there's 0 acceleration. So the net force is 0. That's for A. And B, net torque is 0 if in equilibrium. If not, it's just torque clockwise, just torque counterclockwise.